Okay, so welcome back from the midweek break. Okay, so Lab 9, I made that a little bit of an extension, but this week is the week of Lab 10. Lab 10, technically it's going to show its due this upcoming Sunday, but I've extended its deadline a week after that because it's basically 2 labs in one, but there's just a bunch of extra credit. So it's out of 30 points, but you can score up to 50. So it's a way to get back some of those lab points. Part 1 is about sequences, which will help you simplify basically routing ideas here, which can make your models a lot simpler, and there's a little sort of a less wiring on your models that way. And then part 2 describes batching, signaling, and holding, which we kind of were introduced to back in lab 2, like the muffin oven. Batching can be really useful if you've got like ordering processes. So as you're going to your final projects, and those of you that have customers that generate orders, and then those orders go off and then have to go through a separate process before rejoining with the customer that they're associated with, then there are ways to use these tools to make all of that work. So you can make customers have to wait for their order to finish, for example. You can create batches of orders from one customer. There's a bunch of different things you can do with these. So just in general, especially signaling and holding, there's a lot of interesting additional things you can do with signal and holding inside Arena that like stoplight signaling is actually a thing. You can make it so that traffic has to wait for a turn or a stoplight to change before it starts running again. There's just a bunch of things you can do with signal and hold. So it's a lot of nice tools there. And then also part 2 introduces the process analyzer as well as OptQuest, which can really reduce the time it takes to run simulation models, especially if you're trying to run them through multiple different levels of your decision variables. So things like the process analyzer, you can say, I'd like to run through these 10 different levels of this decision variable or these 10 different configurations. You can load the configurations into the process analyzer, tell them you want to run 5 replications or 10 replications each or 100 replications each, and then hit go, and then it'll just go through and do that for you. So, and then OptQuest kind of goes even further than that. So that's what's going on in labs. Otherwise, the rest of the semester, there's no more labs after lab 10. It's just focusing on your final project. And don't forget, there is that, I think, drop 2 policy on the labs as well, which you can kind of put that into your decision matrix on how you want to spread out your effort towards the applied stuff there. Final project, the next deliverables, again, are in the last week of classes before finals week. So Wednesday of the last week of classes, both your presentation video, there are details on the formats here, but that's basically no longer than 10 minutes. And your final report, there's a 4-page report, not including a title page or an appendix. And that is also due that Wednesday. And then that will give every individual enough time to watch one of those videos and read one of those reports to give a peer review. So that's what's due there at that last week there. Homework H, I think, is set to be due Saturday. And so that's got these 2 questions, one on input modeling, one on output validation. And homework J2, I think, should be available on Canvas. This is one that cannot be dropped. So I've mentioned that a couple of times because we use it to capture some ABET data and a solution set won't be released. But happy to talk about the solutions for that as you, if you have questions while you're completing it or afterwards. So I think then otherwise the ICAs, there's this new ICA here. This is the last ICA. It's called ICA MB. And so the reason I call it ICA MB is there's an ICA MA, which is just a practice version of the pre-midterm it's kind of study ICA. And so that is now available if you want to, I think that's actually been available if you want sort of just practice at those pre-midterm topics. And then this is the post-midterm topics. And so this is meant to be like a final exam review. So lecture M, which is the last lecture before stage 1 of the final exam, then this is due before that to help generate any questions that you might have before that final exam review lecture. So that's the ICA schedule moving forward. And there are sample final exams on campus and other resources. Again, you do one of those lockdown browser compliance tests that unlocks that final exam module, and you'll find sample final exams from previous semesters in there. All right, any questions? Okay, great. So last time we introduced the idea of interval estimation. So from this point on out, I want you guys to estimate quantities whenever the data allow as intervals, not as point estimates. And so if I were to say, what is the, how do you estimate the wait time in the system? You wouldn't just say, well, customers wait on average 4 minutes, because they might wait 4 minutes because that's actually close to what they on average wait, or they might wait 4 minutes because you only ran 2 replications and there's so much variance that they got lucky to wait 4 minutes in these 2 replications, but in your next 2 replications, they wait 40 minutes. So the interval estimate helps combine the standard deviation of basically the variance in outcomes in your estimator with the number of replications you've run as your estimator. And when you combine those together, then you get an idea of, well, how much error do you have in the estimate? How much potential error do you have in the estimate? So if all you know is that you ran 5 replications or more, and that your data, we have this IID, that means independent and identically distributed, IID. So if your data are so identically distributed, if they come from the same sim, they're probably identically distributed. And independent, then likely if they came from different random number seeds in the same sim, they're probably independent from each other. If those are the assumptions you have, then you can use an interval that is bracketed by the standard error of the mean. That's this quantity here. That's the estimated standard deviation divided by the square root of the number of replications there, where the center of it is the mean that you estimate there. And that doesn't tell you a lot statistically. Like, you can't do a lot of rigorous things with that interval, but it at least communicates to your audience, if you were to run this sim or this estimator over and over again, that estimates, this is going to be sort of one SD to the left and the right of this estimate that you got this time around. And so the next time you ran it, then it gives an idea of the distribution of estimates that comes out of your estimator. So that's how you read that standard of mean. So as people say, like, oh, it's the wait time is 5 minutes plus or minus 2 minutes. And then you ask them, well, what is the 2 minutes? They say, oh, that's my standard error of the mean. Or they might just say standard error. That's what they're communicating, is that the next estimate could be, it's like a bell curve. Then that's the one standard deviation of that bell curve. All right, so that's, now hopefully you can do more than that. So if you happen to know that the data that you are using to make this estimate are also normally distributed, then you can form a confidence interval. Typically a 95% confidence interval, but different applications, sometimes it's a 90% confidence interval. If you're a little more exploratory, it's a 99% confidence interval if you're a little more conservative. So the idea here is that it looks very similar to the standard error of the mean. So you still got the standard error here. So it looks very similar to this confidence interval, but we scale it by this critical t value. And this number here will tend to be close to 2 if you have a large number of samples. And so typically if somebody gives you this, but then you find out the data are normally distributed, you can double the width of this interval and you get that. And what this thing tells you are the hypotheses about the variable you're trying to estimate that cannot be rejected by the data. So you're saying that I actually don't know inside this interval what point is more likely to be the true estimate, the true population estimate. But I feel pretty confident that nothing outside the interval to the left or the right is the real population value. So that's what you capture in a 95% confidence interval. That's kind of what we're saying down or here. If you find that your data are not normally distributed, what can you do? Well, if you're lucky enough that if you take that data, like that's why you histogram the data and you look at its distribution. And if you notice its distribution has certain properties, like it could be what we call a heavy tail distribution. So they're not normally distributed, so it doesn't look like a bell curve, but there's a lot of points that are on one side. Then oftentimes what you do with your data, and I'm not going to ask you to do this in this class, but this is oftentimes what you'll do, is you transform that data with a mathematical function, which makes it more normal. So for example, if you've got a lot of really large values, but they're spread out, if you take that data and you run it through a logarithm, so you log transform the data, or a square root, if you think about the shape, if you plot a logarithm or a square root, they look linear for small values, but then they squeeze large values down, like they're a lower gain for large values. And it can be that when you histogram the transformed data, it's normally distributed. And then once it's normally distributed, you can do stats on the transformed data. Now, when you give somebody an estimate, you have to tell them that, oh, this confidence interval, this might be on the transform data. Or once you get the confidence interval, you can then back transform it into your normal space. And it might be that that one half of this confidence interval is actually lower than the other half of the confidence interval, or something like that. So if you can transform to normality, then that is a way that you can restore the statistical tools that you can use. If they're not IID, so if they're not independent, then in that case, you can't even do this thing up here. You can't even use the standard error of the mean, because you'll likely have pseudo replications. So what that basically means is, if you have a sim where you've got a bunch of customers that are all waiting above 10 minutes, and you happen to notice that it's all from one replication of the sim, and there's sort of patterns there where there's autocorrelation. So there's correlation from one customer to the next. If one customer waits a little longer, the next customer is going to wait, also have above average wait, and so on. And so if you get this sort of these correlations there, then you bias your data toward whatever weird thing is happening in that particular part of the sim. It's like you're sampling the same thing over and over again, and you're overrepresenting it in your data. And in that case, we can't treat it as an estimator of anything, because we can't use the replications to give us an idea of how much variance we truly have in the system. So if you do not have independent data, you don't use an interval estimate. Instead, you do use a point estimate, but that point estimate becomes it's sort of a marker of the whole time series. And then you need multiple time series in order to make an estimate. So you could say, well, Monday, I noticed all the customers are correlated together, so I'll get an estimate of the average wait time for Monday, but I'm not going to do any interval estimate there, because it really is just a snapshot of what Monday looked like that Monday. And you do the same thing for Tuesday, and so on. And once you have enough days, if you're pretty sure the days are independent from each other, then you can try to actually start estimating the parameter. But if you estimate things if you combine pool things together that are correlated, then you're not allowed to. Like, there's no good statistical foundation for generating these types of interval estimates, because you're going to get maybe a very, very tight standard error, because everything will be highly correlated together. So you get what we refer to as under dispersion. So if it's kind of like if you were to sample the queue length at a restaurant every second, and you get a time series out, and then you're going back to, or you said, well, actually, no, let's actually sample it every 100th of a second. Well, that's going to increase the amount of data you have by orders of magnitude. But that doesn't actually make it less variable. It just means you've measured it more often. So that's what we mean by pseudo replication. So those are the key issues here. But in most cases, if you're going across replications, it'll be safe to use this confidence interval, and I'll expect you to use that confidence interval. So how is that a useful confidence interval? So this is the general formula here, where we call this thing the half width. Well, here's a little sample example that I did here. It's going to be a little hard to read, but that's okay. You don't need to see the numbers too well, and happy to look at the slides after. But the idea here is I got a spreadsheet where I generated every row has got a bunch of data that I drew from a normal distribution over here in these samples columns. Now, how did I generate normal data from Excel? I used the inverse transform method that we learned before the midterm. So there is in Excel this norm inv, which is the quantile function for a normal distribution. It's the inverse CDF for a normal distribution. And you can say, I want the inverse CDF for a normal distribution, and I want it for the normal distribution that has a mean of 5, and I think this is variance of 0.1. And then from there, then you just drop in random numbers, so numbers distributed between 0 and 1, and Excel will then give you out effectively normally distributed numbers. And if you were to look up in Excel, how do I generate normally distributed random numbers? This is how you do it. It's the inverse transform method, the exact same thing we learned earlier in the class. So I generated a bunch of these data. Forget how many columns this is here, but then I did that multiple times. So you can imagine that the first row is an experiment where I sampled, I don't know, 15 data points that are all happen to be normally distributed. And then I did the experiment again. I did the experiment again. Every row is another experiment. Every experiment, I've got 15 independent samples of a process, which I happen to know is normally distributed. And so from there, I then went and I calculated the mean of every row. And I calculated the standard deviation of every row. And with that standard deviation, I can then use a function in Excel to calculate the half width. So Excel happens to have this confidence.t. Where's the t come from? It's a t-test, so it's saying a half width based on the t-test. That's the traditional half width, the traditional confidence interval. And I pass in the alpha value I want, 5%. So that will give me a 95% confidence interval half width. I pass in the standard deviation, and I pass in how much data I have, the number of replications. And then it will do the half width formula for me. And it gives me the half width here. So this mean plus or minus this half width gives me my confidence interval. And so for each one of these, I know the true mean, it's 5, because I generated the data. Under normal situations, I wouldn't know the true mean, but in this case I do because I generated the data. And so I have one more column here where I said, is 5 in the confidence interval that was generated? And so for this first row, it says true. So that means for this first row, the confidence interval that came from these data happens to include 5 in it. Same thing with the second row. And I did that all the way down here. So I'm just going down through and highlighting all the things I just talked about here. So I do that for a bunch of these rows, and I can see some are true, and then some will come up false. And I'm going to get graphs, which I'm going to look at here on the next slide, that look like this. And so on the x-axis is every row, it's every experiment. And then what you see plotted above it is the confidence interval for that particular experiment. So if I ran the experiment on this particular day, with that, and the data that I got would give me this particular confidence interval. If I reran the experiment on another particular day, then I would get another confidence interval, and so on. So it's like I ran 180 some experiments, and I generated confidence intervals for each. Now I also plot, or know that 5, that's right in their center, this 5 is the true mean. So I can now ask, how often do confidence intervals include the true mean or not? So in this case, this blue confidence interval that I've highlighted here, it crosses 5. So it includes 5 in that confidence interval. So it's sort of successful. If you were to report that confidence interval, you would be telling your stakeholders, I don't know what the true mean is, but it is, I think it's in this confidence interval. And you'd be right. The real parameter would be in the confidence interval you would give to your stakeholders. And if you just gave them the average, and not the confidence interval. So the confidence interval is the blue extent, and the average is this dot right over here. Then you'd be way off the real ones. That's why it's safer to give the confidence interval. It tells you how much error is in your estimate. Now these pink highlighted ones, these are the only confidence intervals that do not include 5. So we see that out of 187 experiments, there were 6 that did not include the right, that falsely rejected the true hypothesis. And that is our type 1 error. We're seeing the type 1 error here. It's written out for us. So this shows us that the t-test works. It shows us if we set the alpha correctly, then we get the results that we expected by going into the t-test. All right, so I'm going to show a couple of different examples of this, what happens when you change the number of replications, when you change the standard deviation, and so on. But any questions about this general? It's going to be a little cleaner than this zoomed in Excel here, so it might be, I think, easier to read. But any general questions about this layout here of what we're seeing here? We've got 100. You wouldn't run 187 experiments in real life. You'd run one experiment, and you get one confidence interval. That you might only have the budget to run one experiment. And it's what risk in that one experiment do you have that the confidence interval you report is not going to have the thing you're actually looking for. And that's saying here it's about 5%. So, and this happens to be, 5% of 200 is about 10. This is almost 200, so it's about 5%. So, you're 95% confident that if you give a confidence interval to your stakeholder, it will be a good representation of the real mean. Okay, so let's see how that plays out here. So I've done that 3 different times here. The difference between these, so actually this is just, this is all 3 of these are the same, but I've got this is basically 300 replications of the experiment instead of 187. And I just did these 100 separate from these 100, separate from these from 100, just so I could highlight that that the idea here is that large confidence intervals always include the real mean. And so if I look here, the FPR is 0.01, or sorry, it's 0.001. So that there is a 99.9% confidence interval. So if a stakeholder said, I want to be 99.9% confident that we have an estimate of whatever the true population parameter is, I want to be 99.9% confident that I know the fraction of the population that agrees with this policy, or I want to be 99.9% confident that the wait time in the estimate of the wait time for these customers. Well, that's going to create very large confidence intervals. It will be the case that only 5% of these confidence intervals fail to capture this true mean, but every confidence interval will be extremely large. And so it doesn't, you do gain confidence, but you also lose precision. So you can say, okay, if you want to be 100% confident, then these are going to be the entire real line. The only way you can tell your stakeholder, I'm 100% confident that this is the wait time, the actual, that this includes an actual correct wait time for the real world system, is if you just allow for any possible wait time from 0 to infinity. That is the 100% confidence interval. The 99.9% confidence interval is quite a bit smaller than that, but it is quite a bit larger than the 95% confidence interval. So that's what we see playing out here. So remember, this is a 99.9% confidence interval. This is a 95% confidence interval, same experiment. So I see here that, so like here, it happened to be that none of these confidence intervals happened to not capture the mean because we only expected 0.1% to fail to capture the mean. Here, we expect 5% of these confidence intervals to fail to capture the mean, and that's what you see. These little magenta dots, those are confidence intervals that failed to capture the true mean. And I just did this 3 times. So in this case, these 3 rows are identical. They just happen to be 100 experiments, and then another 100, and then another 100. And so I'm seeing that I'm getting that 5%. So over here, I'm getting the 0.1%, which for only 100 happens to be the none. So it looks like 0% because I just couldn't run enough experiments to see it. Here, I could run enough experiments to see the 5%. And we can see that that's the trade-off, is that now I have a greater possibility of error. So this confidence interval may not include the real estimate. But when I do report a confidence interval to the stakeholders, it's much more precise. I can tell them that, actually the wait time is between 2 minutes and 4 minutes. Whereas here, it might be that, the wait time is between 2 minutes and 20 minutes. And that's just not that useful of an estimate. So it's a more useful estimate, but it's an estimate that admits more risk. That's what happens as you change the confidence level, as you change the alpha. And likewise, if I go to a really, really high FPR, in this case, this is an FPR 0.6. So this is like a 40% confidence interval. So that's the right here, 40% confidence interval. Now I have really narrow confidence intervals. So I can report to the stakeholder that my estimate happens to be between 1 minute and 1.5 minutes. And that sounds great. But then you have to say, but that's only a 40% confidence interval, which means that I only include the real mean in that tiny interval 40% of the time. 60% of the time, my interval is completely off. And that's what we see here with lots and lots of these magenta dots up here. So 60% of the confidence intervals are wrong. Only 40% actually include the real mean. So if I go all the way up to 100% confidence interval, I get a point, or sorry, if I go all the way up to a 0% confidence interval, or all the way down to a 0% confidence interval, I collapse the confidence interval onto a point. So if you're reporting to someone a point, if you're saying the wait time is 5 minutes or 5.6 minutes, because that's what I got out of here, and you don't give them anything, you're effectively giving them a zero width confidence interval. And a zero width confidence interval is a 0% confidence interval. So you have 0% confidence in your estimate when you only give them a point estimate, which is why you always give interval estimates, because we're never, it's not useful to be 0% confident in an estimate. So that's the idea here. So we get the confidence intervals. As confidence goes down, then so does the confidence interval width. Those two things are related. All right, so now here, these are 3 different examples where, it's the same idea here, but I'm changing the where did I write it down here? Okay, the number of samples. So right here. So here I'm using 20 samples. This middle one I'm using 200. And this bottom one I'm using 2,000. Otherwise, this is a 95% confidence interval in all of these. So notice that here, each one of my experiments, I had more budget, so I could run it for 200. I think 200 was what, this one? Yeah. So here I could run it for 200 replications. Here, I didn't have that much simulation budget or experiment budget. I could only run it for 20. Here, I had enough budget to run it for 2,000 replications. So you guys have already started to take data for your final project. So you know how costly it is to run a real world experiment. Well, running a simulation experiment is also costly in terms of computer time. But imagine this also applies to a real world experiment. If you had to go out and run an experiment every day, it's going to cost you, like this is saying a 20-day experiment versus a 200-day experiment versus a 2,000-day experiment. This is a much more costly experiment or experimental protocol than this thing up here. But what do you get out of it? And what you get out of it is for the same confidence level, so 95%, all 3 of these are 95%, you get that increase in precision. So that's what you're seeing here. So down here, you get really tiny confidence intervals, which is great for your stakeholder. And you can say, and by the way, I'm 95% confident that the real mean is in that tiny little interval. So this interval, the real mean's 5. I can come back and say, well, it's somewhere between 4.9 minutes and 5.3 minutes. And so that's a really tiny estimate, a really tiny error interval. And I'm 95% confident that despite it being so tiny, it actually includes the real thing. So that's the benefit of spending extra, money, resources, or whatever on extra replications. But that's really costly. So it'd be great if we had the ability to do something similar without having to pay for all these extra replications. So that brings us to the variance idea. So if I happen to run an experiment and for 30 replications, so these are 30 replications in all 3 of these, but what's changing from the top row to the bottom row is the noise in the population. So this population noise is 0.5 standard deviation. This is 1. This is 2. So I keep doubling the noise. And as you can see here, my 95% confidence intervals, still 95% of them are right. They include the real mean. So I don't change the confidence level, but the precision of the estimate gets wider and wider with the extra noise in the population. So if you have other sources of variation that you haven't controlled for, then they make for crappier estimates. But if you have the ability to start controlling for variation, you can go the other direction. And that's what we're going to talk about in the last unit, is how to use clever experimental design to use the same number of replications to, and yet reduce the noise in your experiment and get a tighter estimate. So that's the idea there. So that's generally, as an experimenter, you always can increase the number of replications. It's going to cost you. But if you're clever, you can find a way to design an experiment that has less variance in the experiment. So, that might mean it might mean physical consequences. Like I have to shield, I have a room, like I'm taking electromagnetic measurements and of a process that exists in the room, but I've got extra variance from things outside the room. So I might need to shield the room to prevent that extra variance that is unrelated to the process I'm studying from coming in. That's the reason why we have anechoic chambers and Faraday cages and so on, is that they allow us these environments where we can have tighter control over all sources of variance. And we can do effectively the same thing in a computer simulation, is to control all the sources of variance so that we get rid of all this extra noise so that we can go from here to here. All right, so that's the general idea of what a confidence interval is. Question? Well, so the idea here is that I'm trying to demonstrate the risk in a confidence interval. So you would never run 100 experiments. If you had the budget to run 100 experiments, you would do what I think you're suggesting, is to pool all this data and then create one confidence interval from all of this data. You kind of wrap your arms around all of that data and say, no, that's my estimate. Here I'm suggesting, what if you only had a budget for this amount of data, for 30 samples? So not 3,000 samples, you can only take 30. And so I'm saying, well, there's 100 universes, and there's a version of you in each one of those universes running the 30 sample experiment. If we could somehow look across the 100 universes, then we would see that 5% of those universes would have you estimating the wrong quantity. And in 95 of those universes, they'd have you including the right quantity. So how much risk, when you report the confidence interval to your stakeholder, what's the risk that you're wrong? That's what we're trying to capture here. Any other questions about this idea of what a confidence interval tells you? And think about this. Every time a reporter reports on a margin of error or anything like that, the math behind the scenes is exactly this. That's what they mean. If they say that the margin of error for this policy, it's when they say it's within the margin of error, they're saying that the confidence interval includes 50%. If the confidence interval includes 50%, then that means it also includes things less than 50% and things more than 50%. So that means you cannot exclude that the majority on either side of the issue. But at the point where the confidence interval from the polling does not include 50%, then you can safely exclude basically the bottom half of everything less than 50% or everything greater than 50%. And you can say, I have no idea what the true proportion is, but I'm pretty sure that it is above 50% or below 50%. Okay. All right, so where do we get the confidence interval? I kind of mentioned this before in a previous lecture. If you go with, this is what you've learned to do between 380, 385, and here, this expression right here, I calculate a mean, I subtract something off, I take the absolute value, I rescale it, and then I compare that to a number from the back of the book. If we take this expression, this t-test, and we break it up into the two cases having to do with whether the numerator is inside the absolute value is negative or positive. In other words, whether you're less than the hypothetical mean or greater than the hypothetical mean, then we get the confidence interval formula out. So you start with this under the assumptions that X is greater than the mean. You can get rid of the absolute value, and then you can just solve for the real mean, solve for mu. And you get then the lower side of the confidence interval formula, saying that the real mean is somewhere between the estimated mean and this estimated mean minus this half-width formula. If you do the other side, if you say, well, what if the real mean is greater than my sample mean? Then I have to flip the sign of the numerator in order to drop the absolute value. But I can do the same thing, and I get a similar formula. So under this case, then the real mean is between my sample mean and this upper bound of the confidence interval. Combine those two things together, and what it tells you, because you never know what the real mean is, but what it tells you is that if you know the sample mean, and you can make these normality assumptions that go into the t-test, then the real mean is either going to be within this half interval or within this half interval. And we put those things together, and that becomes the confidence interval. And that's why this formula is the half-width formula, here and down here. That's where that comes from. It's just a t-test. It's a geometric version of a t-test. And it captures this idea. So the probability that the real mean is in your confidence interval is going to be 1 minus your type 1 error. So if it's a 95% confidence interval, it's a t-test with a 5% type 1 error. The idea there. And then the one sample rule is if it does not include the hypothetical mean, you can reject it at the complementary significance level. So if a 95% confidence interval does not include a value, you can reject that value with 1 minus 95% or with 5% type 1 error. It's the idea there. So again, geometric interpretation of a t-test. The two sample rule is that if you have two confidence intervals, so you run a sim on your as-is system, you get a confidence interval on wait time. You run a sim on your proposed system, you get a confidence interval on wait time. Compare those two confidence intervals. If they do not overlap, if there's daylight in between them, you don't have to run a two-sample t-test. Because if the 95% confidence intervals, the one sample 95% confidence intervals, if those don't overlap, then it will be the case that a two-sample t-test that you hypothetically could run will reject the hypothesis that the two systems are equal. So that's really nice about summarizing your data with one sample t-test, is that if you have to do a single pairwise comparison, then you can just compare those confidence intervals and you don't have to do an actual test. So that's kind of a nice thing, but you can only do that if there's only two groups. Now, if somebody doesn't give you the 95% confidence interval, but they give you the standard error, and you have reasonable confidence that the data are normally distributed, you can double the standard error, because this critical t value is around 2. And the more data you get, the closer to 1.96 it gets. So 2 actually becomes a conservative estimate. You just double that standard error, and you get an estimate of the confidence interval. So if you get used to staring at confidence intervals, then there's a lot of tools you can use to get a quick idea about whether there's likely a difference between the populations or not. And I think I got like a graphical version of that just showed last time. If you've got two groups, so you can think of this as your as-is system, and you can think of this as your proposed system. You can think of this as wait time. Then what if this is saying that in the as-is system, the wait time is up here, and it's got this standard error. And in your proposed system, the wait time is here with this standard error. Now, your sims are not going to be as super high fidelity models of the real world. So most likely both of these will be simulated data, but this will be from a calibrated sim that you believe is a good match for the real world. So you could say we calibrated the sim, and under the normal conditions in the sim, we get something that is pretty close to the real world. And then that becomes your baseline. So it becomes a simulated baseline. If you make the real world the baseline, then now you've got not only the differences between your the as-is system and your proposed system, but you've also got the sim to real issues, the simulation to real issues like that, well, if I just didn't happen to include every possible source of variance from the real world, then that's an additional source of variance. And so that will make my proposed system look different than my real world system. So this keeps you honest. So when you compare things, try not to compare your proposed systems to real world data. Use real world data to build a simulated as is system and then compare the simulated as is system to your proposed system. That's kind of the normal idea here. And so if you knew these were standard errors and you feel confident that these data are normally distributed, you can double the standard error. So this goes up about, up to around here. This one goes down to around here. And you see that the two confidence intervals that you estimate from the standard errors overlap. So it tells me that even though this looks like this one is less than this one, it could be by chance alone. We could be in one of those universes where it just happens to be the proposed system just happens to just lucky chance do better in this particular run. But if I was in another universe, they might be dead on each other. Or it might be the complete opposite results. So if these instead were actual confidence intervals and not standard errors, they don't overlap. In which case, I feel pretty confident that I'm in the, that I'm likely in one of those 95% universes where this is a real difference. And so I would then conclude that, yeah, my proposed system has a significantly different, less wait time than my as-is system. That's how I might interpret these graphs. Okay, questions about that interpretation? So now when you look at these things, just know these error bars, they tell you more than something about the variation here. They actually help you compare across groups. But that little trick about comparing them graphically, it only works when there's two groups. When there's more than two groups, you've got to get more sophisticated. Okay. So the other things that we talked about you can do with confidence intervals is that if I give you a 95% confidence interval, I'm also giving you the assumption of normality, which means from the confidence interval, you can figure out the half-width. So the half-width, there's a half-width formula there. So if you give me the confidence interval, cut it in half, whatever that width is, if I know the number of replications, I can back out the standard deviation estimated for that population. The middle of the confidence interval is an estimate of the mean of that population. So that means I have an estimate of the cumulative distribution function for the whole population. And that's just going to be the standard normal where I shift it toward my mean and I scale it by my standard deviation. And so in other words, I'm saying, since I know it's normally distributed, I only need two parameters to capture it. And those are my two parameters, the standard deviation and the mean. The mean is in the middle of the confidence interval there. So now that I've got the CDF for an estimate of the CDF for my real data, I can do quantile estimation and all sorts of other things that you can do with a CDF. So the confidence interval, because it also assumes normality, gives you a lot of information about the data set that you can back out. And one thing you certainly can back out is if I gave you, and I think we do this on the lab, if I give you like a 95% confidence interval, you can, if you figure out what the half-width is for the 95% confidence interval, you can divide off by the critical t-value and then apply a different critical t-value. So if you want to go from a 95% confidence interval to a 90% confidence interval, you just divide off the this t-value, which will be the 5% divided by 2 t-value, and then you multiply by the, say, 10% divided by 2 t-value. So you can you can shrink and expand confidence intervals easily if you know the number of replications that went into that confidence interval. Okay, so those are the games you can play with confidence intervals. So any questions of that? All right, so confidence intervals are important to know. You can do confidence intervals on quantiles, which I'll mention here up here, but I do want to mention one other interval that's very important for you to know, especially if you go on and do more stats, the prediction interval. Very similar to the confidence interval, but it has a similar half-width formula, but there's this extra 1 that's out here. So instead of being s divided by square root of r, it's s times square root of 1 plus 1 over r. So what's going on there? What the prediction interval does, the confidence interval gives you an estimate of the mean. And as you increase the number of replications, the estimate collapses on the true mean. It gets smaller. The prediction interval gives you sort of an estimate of the whole distribution. So it gives you an estimate of the mean plus or minus the standard deviation. So the idea here is that you're trying to you can say I already ran, the confidence interval says I ran 10 replications. Where is the true mean? And you could say 95% sure it's in this interval. What the prediction interval says is, okay, I ran 10 replications. Where is the next output of the 11th replication? So it is not trying to necessarily capture the mean, the true mean. It's trying to capture the true variance. It's trying to get an idea of, based on how many replications you've run, how much variance do you think is in the system, so that if we continued to run replications, we went back to the system, how variable, like where might things land? And so that prediction interval starts at the mean, but then the way it works here is if the number of replication goes to infinity, then the prediction interval goes to the true mean plus or minus the z critical value times the true standard deviation. So this kind of gives you an idea of the true variance of the simulation system as opposed to the true mean of the simulation system. So it's trying to predict. So, or I'll say it another way, this formula here, this 1 plus 1 over r, where that comes from is that you're saying there's 2 sources of variance when we do empirical work, when we sample things. There's the fundamental variance in the system, which is the standard deviation, and then there's variance caused by using too few samples. So if you just happen to only sample the system twice, you add a lot of variance because you might have just gotten lucky or unlucky in those 2 samples. But as you sample the system a lot, then you get rid of all the sampling variance that you add, because the sampling variance is like, which 2 samples did you sample? Did you sample these 2 samples, these 2 samples, these 2 samples? And that positional variance comes from sampling. But once you have a lot of samples, then that goes out. You don't have to worry about that anymore, but you still have an intrinsically variable system. So the 1 here captures the intrinsic variation in the system, the standard deviation, and the 1 over r captures the extra variation you get by not sampling enough. And the prediction interval combines those, and it effectively says, based on the data you have, how do we predict? How much predictive power do we have in those previous samples? And you're saying that, well, there's the intrinsic variability in the system, so that reduces our predictive power. And there's also variability due to us sampling so few times. And so that further reduces our predictive power. Once you run the number of samples to infinity, then it collapses on just the natural variation in the system. So what this is saying here is that at some point, adding more samples is not going to make the next run any more predictable, because there's just intrinsic noise in the system that is not from sampling. That's the prediction interval. So we have confidence interval and prediction interval. 2 important intervals I want you to know. All right, any questions about that? So this is what people like to say, PI is a measure of risk. It cannot be collapsed to a point with sampling, whereas a CI is a measure of error. Confidence interval is about error, prediction interval is about risk. Questions about that? Okay. Then I mentioned this last time. We showed examples of this. There is a half-width for quantile estimates. If you wanted to calculate the 85th percentile wait time instead of the mean wait time, then you could run 100 replications and take the 85th replication in the ordering, that would be an okay point estimate, but that's going to have error. So how do we generate, the confidence interval there? Well, this half width effectively tells you which ranks to the left and right of the 85th rank that you end up getting that confidence interval on the quantile. And so that's this idea here. And notice that this thing doesn't depend on the standard deviation. It only depends on the quantile you're trying to estimate, that P proportion and the number of replications. And that just has to do with some, if you have a coin that always comes up heads, it's just naturally going to be less variable than a coin that comes up heads or tails. And this is correcting for that. All right, any questions about the quantile confidence interval? Okay. All right, so then finally, this is where we left off last time. When you have a system that is a terminating system, you're going to simulate it with a transient simulation. You have an experience doing this in Lab 9. And if you want to say, well, how many replications do I need to run? Well, we talked about a power analysis. So if you have a strict requirement on statistical power, you can run a power analysis like you did in that homework. But now that we're using these interval estimates, then you find that sometimes it's easier to communicate to someone the constraints on confidence intervals than it is to communicate power. Now, you don't get any power guarantees out of this confidence interval method, but you still move in the same direction. And so you can ask your stakeholder, what is their desired confidence interval width? So if they say, like you're saying, I'm going to give you an interval estimate of where I think your mean performance is for your factory, for your restaurant, whatever. How tight do you want that interval to be for it to be useful to you? If they say, if you give me an interval that has a 1 minute half width, so it's 2 minutes total, then that's great. You can go with that. They didn't tell you anything about statistical power, but the tighter they make that, the more replications you're going to need, or the more variance you're going to need to reduce. And so, but this helps calculate the number of replications here. So you specify the desired half width, you run a pilot study to estimate the variance, and then you choose the number of replications to keep your half width down. And we said the formula you can use for that, start with the half width formula, you back out the number of replications from this, you get this ugly quantity. But if you assume it's enough replications that your T statistic looks like a Z statistic, a Z table, a standard Z table, then in that case, you just look at the Z table, which doesn't depend on replications. So if you ran your pilot study and you estimate the variance or the standard deviation in your system, you have the half width your stakeholders asked you for, and then you scale this by this Z and then square it, just apply this formula, then that tells you the number of replications you will likely need to meet their constraint. So if you ran 10 replications in your pilot, this thing spits out 15, then you can run 5 more replications. If you don't happen to get quite to the tightness that you're looking for there, you could maybe run another 5 replications. But that's the idea here, is it gives you in the ballpark of where the half width, of how to get the half width in the neighborhood of what your stakeholder wants. So that is a way that for transient simulations, how you can choose a number of replications. You can either do it by a power analysis or this half width constraint, which it's a little easier to do this half width constraint, but it doesn't give you any guarantees on power. Questions about that? Okay, great. Okay, so let's do one of these. Okay, so poll should be open so assume you've got 5 samples. So the same set of 5 samples, and assume they're normally distributed. Which of the options below will be the largest confidence interval? The confidence interval that is it's the biggest. So from the lower bound minus the upper bound is the largest. Is it the 1% confidence interval, 10, 85, 95, 99, or does it depend on the data? So go ahead and clock in your answer. All right, I'll give you maybe 10 more seconds. It's probably got to be A or E, right? You know, so it's probably not something in the middle, and it's probably F. F's the distractor. So it's really, is it, is 1% small or is 99% small? So the question, or is 1% large or is 99% large? All right, so I'm going to go ahead and hit stop. Results for that one looks like most people chose 99% confidence interval. And so the idea here is that, how do you gain confidence? You include more possibilities. So that's right, that the largest confidence interval here is the confidence interval that has the largest confidence. So a 1%, a 0% confidence interval is a point, and a 100% confidence interval is the entire real line. So that's how you get that. So if I were to give you a 95% confidence interval and ask you to convert it to a 90% confidence interval, then you would be narrowing the confidence interval. So you are now saying, all right, I'm going to give you a tighter estimate, but I have less confidence in the estimate. Any questions about that? All right. So, all right. So this stuff here, there's just a few more things we need to add to deal with steady state simulations. And so the idea here is that now we're working with a non-terminating system, and yet we have to simulate it with an effectively terminating system. So our sims have to start, they have to end in order for us to make an inference. But the steady state properties of a non-terminating system are theoretically infinite. So we have to deal with that. And so if we are using a system like this one to estimate the properties of something that's effectively infinite, then we need to be very careful about how we start this system and how we end this system. Because if we end it too soon, then we may not have enough data, like the really meaty data that we want to sink our teeth into, which is here. And if we don't start it the right way, we might corrupt the good data with a bunch of bad data that is totally irrelevant to our non-terminating system. So those are the key questions here. How much data to get rid of up front? How much data do we truncate? And you saw that in lab 9. And then the new question is, you can say, do we want more replications? That's a question we already had with the transient sims. But the other question we have now here is, how long of an execution time do we want? So it's not just how many reps we run, but how long does each rep run? Which, if you run a replicate, if this is a 24-hour sim, and now I make it run for 48 hours, 72 hours, and so on, now every replication is going to take longer. So there's a computational cost there to making these run longer. And then can I combine these two bullets together? And that's what we'll close. And we'll, if we don't get there, we'll close. We'll start with that next time. Is that can I somehow run a single replication? So I only have to throw away data once, but run that replication for so long, I can cut it up into independent pieces and treat them like independent replications. That's batching, which we'll get to here again at the end. All right, so here's the general problem. Someone says, I have a non-terminating system. I have a 24/7 emergency department. Things are always happening. It never closes. It never technically opens. There are rare events where it has to shut down or whatever, but we're not interested in those. We're interested in 99% of the year, the rest of the year, when it's just open. And so how do I'm trying to model properties of that. And so I'm interested in steady state properties. And so what do we mean by a steady state property? We're saying that, like, if you've got a system that has discrete data that are generated, time period after time period. So this could be inventory data, for example. So I'm interested in what's the steady state inventory for a system that is constantly processing, like an Amazon warehouse. It's just constantly open. And so every day I can measure the inventory. And so I get this sort of discrete thing here. And then so over, I can take an average inventory over any number of days. And then I can take that number of days to infinity. And then that would give me my steady state inventory level. So there might be variation in every 10-day group, every 10-day average. But if I take that number of days out to infinity, then it levels out and I just get the sort of background inventory level. And I can do that with continuous time stuff as well. So if I've got something I can measure at any instant of time, I could take the time average over an interval, but then I can take that interval to infinity and I can have the infinite time average. Those are steady state properties. And what's nice about taking things to infinity is that there's any little like perturbations, if there's any little weird shocks to the system, they just get averaged out. They're washed out by the abundance of nominal data, of more normal time data. And so transients, they naturally get filtered out of these systems. That's what we're trying to estimate for the real system. But we're using a system which is not that way. We're using a computer system. Computer system, that world that we're simulating has to start, it has to end. We're going to allow ourselves to delete some of the early data because it's unrealistic data. And we're going to allow ourselves to stop at some point, but we don't know what time to stop. And so if we're estimating this discrete time estimate, then we're going to take an average without taking n to infinity, because we can't do that. It has to stop at some time. But we're going to start counting at d time steps in. And so this is our warm-up period here. We're getting rid of d steps of data is the idea here. So yi, the first data point that actually goes into this average is yd plus 1. That's the idea there. So we're deleting data up front, and we're choosing how long to run the sim. Similar idea when we take time averages. We can take a time average at any particular point in the sim, but the early points are not realistic because it's effectively a transient simulation that we're using to try to estimate a steady state value. So this integral is going to start at some point in the middle of the sim and go to our endpoint. And so the interval here, in this case, is TE. And so we're going to average over that time interval, but we're going to start the interval late. And that's how, so it's the same idea in both one of those things. So that's how we do that. So now we have to decide where to start and where to end. Okay, so already talked about this problem. Early simulation transients create bias. How do we get rid of that bias? Get rid of those transients. The common solution is to reduce our transient lengths with intelligent initialization or use a warm-up period. So what do those two things look like? Those of you taking 470 right now, this is a good use for the tools that you learn in 470. If you're working with queuing systems, for example, the average values that you get out of that. So you set up your network or whatever, and it says, on average, we expect a queue length of around 6. And so you'd say, well, if the mathematical model expects an average of 6, maybe I should start my system with 6 people in the queue. And it's true that my system is going to vary, whereas maybe the 470 system won't. But so my system might go up to 8, might go down to 6 or 2, but it's probably going to fluctuate around the value, or at least close to the value that the back of the envelope calculations from 470 give me. So that's one of the things that I can use that for, is to say, run a coarser grained mathematical model to give me a guess at what my initial conditions should be, and then use those initial conditions. By default, we usually set our initial conditions like 0. There's 0 people in line, there's 0 people in any of the queues, there's 0 people in the system. All of the machines are brand new in our sims. That's normally what we do. But what we're trying to do is say, well, actually, why don't we say that, some machines are brand new, other machines are near failure. Those are the types of things. Come up with an intelligent way to initialize our systems so that they start closer to where we think they're going to end anyway. And that'll reduce our warm-up period. The other idea is then, once you've done that, then delete the warm-up period. And so find a time period here where you're saying that these are our real initial conditions here. These are the initial conditions we guessed but we're wrong at. And so we're going to pitch these. So then the question is, how do you know you've reached the real initial conditions? And so we played with that a little bit in Lab 9. So you can look at, for example, this is, I think, from the factory, but somewhere here I actually said where this is, but it's from one of the systems we gave you during Lab 9. This is from a replication of that. And you can see that, this say is, I don't know, Q length or something. And so it's constantly kind of going all around. If you look at this, you can sort of say, well, if this is time 0 over here, where is our warm-up period end? And you look at this and think, maybe it ends here because maybe this is a big transient. But I don't have a lot of confidence in that. So I can do things with that. Like I can do a cumulative average. And so the idea here is, what if I create I average up everything from a certain time period back? So this is what the textbook does. And the dark line, I know it's hard to see here, but the dark and more variable line, that's the actual replication out of the sim. And the light line, that is where you've averaged it, where you're saying that I'm going to take a window of time and I'm going to produce the averages of all of the real data and then output that average. And so that smooths things out, that filters things out. And maybe then in this smoother portion, it's easier to see that, okay, maybe the transients ended around here. So that's one thing you can do. You can just filter your data. And then, but you see, but I'm running multiple replications. So maybe I can leverage the fact that I've got different replications that are independent from each other and use that. So if I've got multiple replications, like from Lab 9 here, so this is different initial seeds, all time 0, but they all go different ways. What if I average across them? So that's what we've got here. And the idea here is that I'm not averaging across time, I'm averaging across replications. And so the dark line is the mean across replications. The light line are the confidence intervals around the mean. And so now this little confidence interval tube, it starts low, it gets kind of high, and you see, across all my replications, things look like they settle down right around time 100 here. So anything from this point on looks pretty normal. This kind of has a bend in it. So maybe we're going to call this the transient period. So now we're averaging across reps. And then, you can average that moving average as well. So you've got an average across reps, and then you can also average across time and smooth that curve out. It's not an exact science here, but the point here is you can use different filtering techniques to give you a better guess at where these things might end. And you then want to try to make a conservative estimate from that guess. So you could say that based on my educated opinion, at around time 100 is where every replication seems to start looking like it's reached its steady state. I'm now going to maybe multiply that by 2. So I'm going to have some safety factor that I add into that. And then I'm going to discard that amount of data. And I feel pretty confident that that discarded data is going to be, is going to work out. So that's the idea here. So I'm not expecting you to memorize all of these different filtering techniques, but I just want you to get the essence of, you can average across time, you can average across replications, and then you can average across time across replications. And those are ways you can smooth out these data. All right. Now we'll wrap this up. There's not much more left here, but we'll wrap it up at the beginning of next time. I'll give you one more clicker. So after batch means, yeah, this is a good one. So I'll do this clicker now, and then we'll see you next week. Okay, so question here: which of the following? And I guess I'll help you on this because I make this in the couple of slides we skipped. I try to drive this home a little bit more, but we've talked about this already. Which of the following is not affected by an increase in independent simulation replications. And this isn't graded for correctness, but is the 95% confidence interval not affected by reps, the mean estimator variability, the computational time required, or the estimator bias, or are all of these things affected by how many replications you choose? So I'm looking for which one of these can you not get rid of by adding more replications, or which one of these is not affected by more replications. Regardless of how many days I teach this class, that will never be affected by the number of days.